Hello everyone and welcome to my presentation on visible difference predictors, a class of metrics based on perception science. My name is Alex Shapiro and I'm part of the applied perception science team at Meta. So designing display systems that have good image quality is an important problem for scientists and engineers. And practical displays are not perfect, we know that. There's always artifacts we have to work around. So here's some examples of artifacts, like display artifacts that are relevant, especially for head-mounted displays like virtual and augmented reality. We have things like blur, color fringes, maybe due to the optics, reduced contrast, chroma subsampling, dither, light source non-uniformities due to the pixels, waveguide non-uniformities if you have a waveguide optic in front of your eye, and then correction errors that sometimes stem from inaccuracies in the eye tracker when trying to correct for waveguide errors. So all sorts of different things that can happen to your image due to the display. And each one of these artifacts has to be managed. And we'd be interested in our minds of setting some sort of model like this, where we're thinking about the feasibility versus the image quality impact of each of these artifacts, the feasibility to remove it, that is. So in terms of the image quality impact, you can imagine that you could have very little impact where you basically can't see the artifact if it's very subtle, or it could just look terrible if it's too strong. And in terms of feasibility, removing this artifact could be completely impossible, just too costly or too difficult, too computationally intensive, or it could be easily doable, right? And typically you'll have some sort of trade-off for every artifact that'll go between removing the artifact completely would produce excellent image quality, but not too feasible, and then leaving the artifact just untouched would be easily feasible, but would have some sort of large impact on the image quality. So we wouldn't want to do the first thing just to avoid infeasible solutions. We wouldn't want to do the second thing to avoid bad image quality, and we're trying to find some sort of sweet spot, some sort of good trade-off to hopefully have an acceptable solution in both of these ways. Now, for this talk specifically, we're interested in how to quantify, how to answer this question, whether an artifact has acceptable image quality or unacceptable image quality impacts when it's either present or it's being reduced to some extent or worked on. And for that, there's different ways of performing the assessment to try to understand whether that's the case or not. So, for example, one way that everybody probably is familiar with is to run a subjective study, so a user study. Of course, that's the most accurate one because people will be looking at the artifact and really sort of rating it and talking about whether it's good or not. But it can be slow and expensive. You have to find all these people, train them, create tasks that are appropriate, gather data sets, and so on. And further, you also need the hardware and the software to actually be available for people to look at it. And that's not always true when you're doing development. Now, there's another version, which is a GoldenEye study. This is maybe a little bit less onerous, but could still be somewhat accurate. You bring a person who is, this big, this big experienced engineer or something like that, and they, have just, lots of experience with this problem. Now, the good thing here is that it can be fast because you don't need to find so many people. You just bring one or a few people who are big experts in the field, but it does have this single point of failure and still has this problem of the hardware and the software being available. So it's a bit faster, but still somewhat onerous. Now, the third and kind of the easiest way of assessing image quality is automatic, right, through algorithms, or as we call them, metrics. Now, these can be fast and cheap because you're just running a program. It can run on a large data set, can run for all night or as long as you need it to. You can simulate hardware and software that isn't physically available to you in prototypes yet, right? So you could simulate all sorts of things and try to get an answer for hypotheticals. And there's lots of options for different metrics, different types of algorithms. But the question here is this metric, whichever metric I'm using, reliable for my problem? Is it actually going to predict what the GoldenEye or what the subjective study would have told me if I had had the chance to run those? Now, there's one more thing about metrics that is really useful, which is even if they're not perfectly reliable, they're still great because they can at least help you narrow down your design space. So imagine I have some sort of design space, like maybe it's a display and I have different options for that display, different components or whatever it is. And I need to analyze them. Oftentimes you have combinations of those and they can grow to a really large extent of possibilities that you may hypothetically be interested in, all of which will have effects on the artifact you're thinking about. Now, when you run the metric, even if the metric isn't perfectly accurate, you could sort of put together a table of all your design options, which you could end up with many, and then run the metric, get some sort of assessment that is at least partially correct, and then use that to just simplify your trade space. Just pick some of these options that are, remove the ones that are clearly bad. Leave the ones where there's some room for, for uncertainty for finding the right answer. And then you can still run a smaller, more targeted user study on those, right? So that could be another way to leverage metrics. Very well. Now I'm going to talk about some metrics that I think most people are familiar with. This doesn't mean that these are, the only metrics present, and some of them are, pretty traditional, metrics introduced a long time ago. But I'm discussing these ones because these are the ones that when I go to conferences and I talk to engineers, these are the ones that are familiar with most of the time. And if you want a more full treatment of metrics, you can go to our published works and read the related work section, which will have like a really in-depth conversation about all metrics in the literature. Now, so these metrics here, PSNR, SSIM, and MSSIM, CIE delta E, and LPIPs, they're very popular. And I'm going to talk about some of the features that they may or may not have. Now, the first feature I want to talk about is display geometry. And none of these metrics has coverage for display geometry. Now, what I mean by display geometry is really the physical location and size of the display in relation to the viewer. So imagine you're looking at something like a monitor or a TV in your house, and it covers a certain area of your field of view, and you're showing, let's say, a 1080p image on that display. And it might look, something like this, like what's represented by this Y square. But if I show that same 1080p image on a phone, on a handheld, smartphone, it would look like that. And if I showed it in a VR headset with a wide field of view, it would look like that. So those are pretty significant differences. And you can imagine that if you want to correctly account for things like the frequencies present in the image, like the detail and the scale of that detail in relation to the user, you would have to know about the display geometry and account for it. And none of these metrics is able to do that. Another point is the display photometry. So what I mean by that is, what is really the display's brightness? Well, I know the pixel values, they can be, let's say, normalized and scaled from 0 to 1 or something like that, but how bright is the actual display? Is it 100 nits? Is it 1,000 nits? Is it 10,000 nits, right? What is this actual physical contrast, right? What is the color space? Like defining the display rather than just thinking of pixel values can be really important to accurately represent displays that are darker or dimmer or more or less colorful. And yeah, one important point is that these have been changing a lot over the last few years. So, assuming something traditional like a CRT display from the early 2000s just may not be very representative anymore of the use cases we're interested in, especially when it comes to things like headsets. Okay, now for the other part, this is about spatial features and color. Now, most of these metrics don't do color, and the ones that do, like delta E, they don't account for spatial features. And what do I mean by that? So delta E was kind of built with this kind of question. People would be looking at a flat field that is bipartite, separated in two parts, and sort of matching the sides. That's how this metric was developed. Now, I could have an image here. For example, we have here a flat field on the left side, just a gray field with nothing. And on the right side is the same field, but distorted with some chromatic noise. And you can see an inset showing kind of a zoomed in version of that image, so you can see it more easily. Now the mean delta E here is 30. I'm going to take this image on the right, and I'm just going to redistribute the pixels. All the pixels remain within the image, but now I've sorted them from top to bottom in terms of brightness. Okay, and now you get an image that to me looks much closer to the one on the left. It kind of looks like a flat field. The pixels are still there, but the noise haven't been replaced with kind of a ramp, just made all the difference. And here they are side by side. Left side's the noise, right side is the sorted noise. And delta E will just give you the same answer for both of these. So that's what I mean by saying that the metric does not account for things like features on the image. And here's another example of that. These are some Ferris wheels that have been distorted with different types of artifacts with noise, saturation, and white balance, just to tell you that it's not all about just knowing whether it's noise or not. Like in this case, the noise, for example, isn't very visible. It's kind of masked by the features of the image, unlike in the flat field. But the saturation and white balance are quite visible, and delta E will just give you the same answer for all of these. Okay, and this sort of artifact isn't theoretical. We encounter these things a lot in industry. For example, when dealing with waveguide non-uniformity. So if you have optics in your headset, they might create these kinds of colorful patterns that are shifting even temporally, and those are things you ideally want to account for correctly to predict whether this artifact is visible, to try to predict the results of that subjective study that you could have run. So, well, that kind of gets to my last point, that none of these metrics are video aware. In other words, none of them are aware of the temporal characteristics of your artifact or of your content. They all just operate on frames. And if you have something that changes over time, well, you'd better be able to account for that as well if you want to predict it. So today, I want to reveal to you guys something new, something special, something hot off the presses. In fact, it hasn't been presented yet academically, although it has been accepted to SIGGRAPH later this year. And what it is a new video metric that is solving a previously impossible problem, which is color, right? You might have guessed from what I've been saying so far. We call this metric color video visual difference predictor. So it's a metric that is color aware. It serves for video, so it does both spatial and temporal features, and it's a VDP, which I'll talk about in a second. Now, on this table, it's the only metric that can do display geometry, photometry, accounts for spatial features, color, and also for temporal features or video. Now, when I say it's a visual difference predictor, what I mean is it comes from this tradition of work that has existed in our field called the VDPs, the first of which was introduced by Scott Daly in 1992, and then a follow-up for HDR-capable follow-up was introduced in 2011 by Professor Mantiuk, my collaborator, and some colleagues. And then later, Meta and Professor Mantiuk, we've introduced a foveated version of that. And now we're introducing also a color-aware version, which is most of what I'll talk about today. So very well, the philosophy of VDP is first, we'd like to match data from human studies. We want to make sure that it really matches existing data from actual subjective studies. The second priority is that it has good computational usability, that it runs fast, that it's easy to use, and that it covers relevant engineering use cases. And the third is also to do some plausible modeling of physiology, of human vision. Okay, so it's not so much based on just some sort of algorithmic or mathematical concept. It's based on how we believe human vision actually works. And what that means is that these are also white box metrics. Okay, so nowadays, of course, with things like deep learning, for example, being very popular and producing great results in many fields, nonetheless, we think there's a lot of value for metrics to consider making them white box and interpretable, where every component can be understood and checked, rather than having them be trained. Because that means that hopefully, when we go into artifacts that our metric hasn't encountered and we try to predict those, we still do a good job, because we try to build the algorithm based on how we think human vision works, rather than training it to reproduce a certain set of data. So today's ColorVideoVDP work is a product of 3 years, or more than 3 years really, of research and development by Meta and the University of Cambridge. And on this slide, you can see my co-authors and collaborators for this project. And I'll go through a very quick overview of how the algorithm works. First, we take the test and reference image, and both of them go through the same pipeline until a later point when a difference is taken. And the first step of that pipeline is the display model. So this is where we model that display geometry and photometry. And in practice, in the software, the way that's done is with a template like the one shown here. So you can input the specifics of your display pretty easily and model whichever display you're interested in, including its location towards the user and all of that. The next step is converting into opponent color channels that are modeling how human vision works for color. After that, we do a temporal decomposition, and this one has a sustained and transient channel for luminance, and then 2 color channels for the chromatic portion. And this is based on the vision science of how our temporal vision works. Following that, we have a multi-scale decomposition, which is achieved by means of a pyramid. This is in order for us to be able to predict whether distortions will be visible at a coarse or a fine scale. Finally, we applied the contrast sensitivity model, which is shown here, and we had to develop this model anew in order to account for all of these different aspects of vision that we wanted to model. So there wasn't one that fit the bill, but we were able to develop one for the purpose of making this metric, which we call Castle CSF. This is the kind of model that predicts whether a certain distortion will be visible to a user or not, based on all of these different parameters. And then finally, the Castle CSF results are also augmented by using a contrast masking model, which is kind of a concept that will help explain whether, for example, noise would be more or less visible on a busy background than on a flat background. And we saw earlier today in the presentation, a noise that is very well visible on a flat field may become invisible when it's on a busy image. So this is the kind of problem that the contrast masking model helps us accurately predict. Finally, the results of all these transformations are pooled and then regressed into what we call just objectionable difference, or JOD scores. And they're calibrated on a big number of data sets. I mentioned earlier that we have one of our priorities is to make sure that our results match the outputs of subjective studies. And so we've calibrated this metric on as many studies as we could. And the first one here in this list is one that we've created specifically for display artifacts, which contained 14 different scenes and different use case scenarios. Those 8 artifacts that I've mentioned earlier in the presentation, each one sampled at multiple levels of magnitude and also a reference. And so this is, to my knowledge, the most complete data set of display-specific artifact distortions out there. And we made sure that our metric works for all of these really well. We've also calibrated on other data sets that are more traditional and have things like video compression and other types of distortion that are popular in the literature. So finally, I mentioned the metric is scaled in these just objectionable difference units. And this is an interesting aspect of our metric, that the output is in actually meaningful units that you can convert to things like percentage preference. So for example, if your result is 1 JOD off from the reference, it's 1 JOD away, that means 75% of the people will prefer the reference, and 25% of the people will not notice, and they'll choose the distorted version. So it gives you a really good intuition when you get a score of how bad the artifact is by converting it to a percentage preference and sort of going from there. Okay, so now for a quick roundup of some results of ColorVideoVDP. In our tests, ColorVideoVDP outperforms other metrics on both old and new data sets. And here's a really big table that we've included in our supplementary material of performance. You can see there ColorVideoVDP at the top with the best performance. And we've compared it against every single metric we could get our hands on, including things like SSIM, delta E, flip, all sorts of metrics that we could find, okay? Including also deep learned metrics and white box metrics, everything under the sun. Another thing is it runs pretty quick on a GPU and can process really high resolution images and videos. Here's a plot on the right of the time that it took to process 50 video frames, okay? And on the x-axis, we have different resolutions that we've tested this on. And on the y-axis, we have time. So you can see, for example, that for a 1080p video of 50 frames took about 1 second to process it, or just over a second. So it kind of works sort of at a near real-time rate for those when running on a nice GPU, which is actually pretty quick for a metric, okay? Finally, this is sort of reaching the end of my presentation here, so I just want to mention to you, ColorVideoVDP is live on GitHub now. It's an actively maintained repository. We have lots of documentation and example codes, templates for common display types, and you should have no trouble getting started if you're an engineer or researcher who wants to use this. You're very welcome to, and we've tried to make it as easy as possible for you to do so. And I'd like to also mention once again and thank my colleagues and collaborators. And with that, I finish my presentation, and thank you for your attention as well.